All right, Chapter 1. Chapter 1, Practice 3. You asked for the following questions: 3, 4, 7, 8, 11, 17, 18, 19, 20, 21, and 22. So I'm going to do all of these on one video. Fast forward to the ones you need. Starting with number 3. Find the limit numerically. Numerically means table. First thing, if you're having trouble typing this in, please type it in your y equals screen. You need to put a parenthesis and then 1 minus. If you hit the math button, you will see a cube root button. And so we'll type in x. And then I close my parenthesis, and then you'll hit your divided by sign. And then once again in parentheses, you're going to put x minus 1. So that is how it's going to go into your calculator. We need to approach, it said to find the limit as x approaches 1. So I know I need to make myself, make myself a table. Sorry about that. And I'm going to put 1 in the middle here. And I know that I need to approach it from both sides. So I'm going to put 0.999, 0.99, 0.9, and then going the other way, I'll have 1.001, 1.01, and 1.1. So if I go to the table feature of my calculator, it's just second graph, and type in 0.9, I should get negative 0.3451. For 0.99, I get negative 0.3345. For 0.999, I get negative 0.3334. For 1.001, I get negative 0.3332. For 1.01, I get negative 0.3322. And for 1.1, I get negative 0.3228. So as I'm coming in from the right and as I'm coming in from the left, I notice to 3 decimal places, my limit would be negative 0.333. If I wanted to simplify that, I could to negative 1/3. All right, next problem is problem number 4. Once again, we're going to use an example to show the following statement is false. So this problem says if the limit as x approaches 4 from the left of a function is equal to 2, then the limit as x approaches 4 of the function exists. So basically what we're trying to show is just because the limit as I'm coming from the left is equal to 2 does not guarantee that my limit exists. So the way that we're going to do that, we're going to show that the if part is true, and then we're going to make the then part false. So I need to be approaching x equals 4 from the left, and as I'm approaching, I have to be approaching a y value of 2. So I'm just going to be coming in, la-di-da-di-da-di-da-di-da. Okay, I think I'll even put a point there. So I'm coming in from the left. Okay, the thing is that now though, I don't want the limit to exist. And we know the limit does not exist if the limit from the left does not equal the limit from the right. So now I just need to make my limits not equal each other. So I'm going to do something like that. So notice even though my limit as I'm coming in from the left is equal to a y value of 2, as I'm coming in from the right, I'm not getting that same limit. So my limit does not exist. All right, next problem is problem 7. Okay, this one tells us that f of x is equal to 1 over x minus 1, and g of x is equal to x squared minus 2. And first of all, it asks us to find f of g of x. So basically, we're just going to take our g function and put it in for the x value. So I'm going to get 1 over x squared minus 2 minus 1. That will simplify to 1 over x squared minus 3. Okay, part B, that was part A. Part B asked me to discuss the continuity and use the words removable and or non-removable. Okay, we know that this function will be discontinuous when the denominator equals 0. We're used to something that we can factor, but it's really not a big deal if we can't factor it, because basically we just need to figure out where does that denominator equal 0. So I'm going to put x squared minus 3 equals 0. And then I'm going to actually add 3 to both sides. And then I'll square root both sides. So we will get x equals plus or minus the square root of 3. Okay, so those are the values that are going to make the function undefined. So that's where it will be discontinuous. And notice there was nothing to cancel the x squared minus 3 with up in the numerator. So both of those will be non-removable discontinuities. And of course, on my test, I would definitely write it out in a sentence that there would be non-removable discontinuities at x equals plus and minus square root of 3. Okay, problem 8. It says to explain why the equation x to the 5th minus x plus 1 equals 0 must have at least one real solution, and I added to the question on the interval -2 to 0. Okay, if it has one real solution, that means there is a place where the function equals 0. And if we want the function to equal 0 and I'm given an interval, I know that this is a candidate to do the intermediate value theorem with. So what I'm going to do is, first of all, let's go ahead and find the function. We'll just call this function f of x, even though I didn't call it anything. Let's find f of -2. And when I plug -2 into the x values, I will get -29 as an answer. And then when I find f of 0, if I plug 0 in, I will get 1. So I could say, since f of -2 is less than 0 and f of 0 is greater than 0, then by the intermediate value theorem, there must be a place where the function, there must be a place or an x value where the function equals 0. And that's again due to the intermediate value theorem. All right, next one, number 11, where we're actually finding a limit and we don't get to use our calculator. So we have the limit as x approaches 0. My function is 5x minus 2 over 1 over x squared. All right, if we don't get to use our calculator, this is one where I showed you if we have a division sign, we can just set this up as two separate problems. So we're going to find the limit as x approaches 0 of 5x minus 2, and then we're going to divide it by the limit as x approaches 0 of 1 over x squared. Okay, and we're going to treat this totally separate. First thing that we should always try to do is just plug in the limit. So we're going to try to plug in 0, and on this one I can plug in 0, and when I do that I get -2. This one, if I try to plug in 0, I get 1 divided by 0, so it just doesn't get me anywhere. So instead, I'm going to remember what the graph 1 over x squared looks like, which is this. And then I need to think, as I'm approaching 0, coming in from the right and coming in from the left, I notice that I'm heading up towards infinity. So the limit of that problem then would be infinity. And -2 and divided by infinity, I'm taking a number and I'm dividing it by a really, 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 really big number. And if I'm taking a number and dividing it by a really, really, really big number, that number will get closer and closer and closer to 0. So my limit for this problem would be 0. Okay, next problem, number 17. Once again, finding a limit. It says to find the limit as x approaches 0, square root of 4 plus x minus 2 all over x. First thing that we always should try to do is plug in 0. So if I plug in 0, I end up getting the square root of 4 minus 2 over 0. The square root of 4 is 2. 2 minus 2 is 0 over 0. I cannot find the limit that way. It doesn't mean that I don't have a limit, though. I do notice that I have a square root. And when I have a square root, I know to use the rationalization technique. So I'm going to multiply by the conjugate, 4 plus x plus 2. And then I have to do the exact same thing in the denominator. Okay, up top, when I take the square root of 4 plus x times the square root of 4 plus x, I'm going to get 4 plus x. Minus 2 times 2 is 4. All over. Do not do anything with the denominators, just put them together. Okay, next thing I notice, 4 minus 4 is 0. So I'm left with x over x times the square root of 4x plus 2. I now notice I can cancel the x's. So now I have 1 over square root of 4 plus x plus 2. And then from here, we're not done because my whole goal was to find the limit as x approaches 0. So now we're going to plug 0 in for the x. So now I have 1 over square root 4 plus 2, which is 1 over 2 plus 2, which turns into 1/4. So my limit is 1/4. All right, moving along to number 18. Okay, 18, discuss the continuity, and we're going to do a removable, non-removable, vertical, horizontal, whole. Okay, so we've got 7x plus 14 over 2x squared plus 4x. I see lots of things that can be factored, so I'm going to factor. 7, quantity x plus 2, and the denominator 2x, x plus 2. I notice that my x plus 2's can cancel. All right, that's going to set us up. First of all, let's look at vertical asymptotes. Vertical asymptotes would occur at non-removable discontinuities. I noticed that when x equals 0, this function would be undefined, and it did not cancel with anything in the numerator. So I would say there is a vertical asymptote at x equals 0 because of a non-removable discontinuity. And I definitely would use complete sentence when I did this on my test. And then I'd next talk about a hole. I know that there's going to be a hole. X equals -2 would make this function undefined. However, it could cancel out. So I know that there's going to be a hole at x equals -2 because of a removable discontinuity. Okay, the last thing it asked me to mention was the word horizontal asymptote. And horizontal asymptotes are not the same thing as horizontal tangent lines. If you refer to your 3-5 notes, a horizontal asymptote occurs when I'm finding the limit as x approaches infinity. So if I go back to my original problem, I have 7x plus 14 over 2x squared plus 4x. To find the limit as x approaches infinity, I compare the degrees in the numerator and the denominator. I notice that the degree in the denominator is bigger, and when that happens, I know my limit is 0. So there is a horizontal asymptote of y equals 0, and that is because the limit as x approaches infinity is equal to 0. Okay, problem 19. It asked me to find vertical and horizontal asymptotes and to explain why. We've got f of x is equal to x squared minus 5x plus 6 all over 2x squared minus 8. Okay, I know for vertical asymptotes, I'm looking for non-removable discontinuities. So let's factor x minus 3, x minus 2 all over 2, x squared minus 4, which reduces to 2x plus 2, x minus 2. I notice that my x minus 2's cancel out. So I'm looking for non-removable discontinuities. I know on this one that x equals -2 would make my function undefined, and I could not cancel it out with anything in the numerator. So there will be a vertical asymptote at x equals -2 because of a non-removable discontinuity. And I definitely on my test would use complete sentences when I was doing this problem. All right, the other next thing was horizontal asymptote. A horizontal asymptote is not the same thing as a horizontal tangent line. If you refer to your 3-5 notes, a horizontal asymptote occurs when the limit as x approaches infinity. So we're going to go back to the original function to find the limit as x approaches infinity. We're going to compare the degrees. The degrees are the same in the numerator and the denominator, so our limit will be the ratio of the leading coefficients. There's an invisible one there. So the ratio of our leading coefficients is 1/2. So there is a horizontal asymptote at y equals 1/2, and that is because the limit as x approaches infinity is equal to 1/2. Alrighty, problem 20. Find C so that f is continuous. Well, we've done lots of problems like this lately with f being differentiable. The differentiable just goes one step farther. Okay, so for this one, if it's continuous, we know that the limit as x approaches 2 from the left would have to equal the limit as x approaches 2 from the right. So to find that, let's just plug 2 into the left equation. So 2 plus 3 would give me 5. The limit as x approaches 2 from the right, let's plug it into the right equation, and that would end up being 2c plus 6. In order for this function to be continuous, the limits have to equal each other. So we have 5 equals 2c plus 6. Now we can just solve for c. So subtracting 6, I get -1 equals 2c. And if I divide both sides by 2, I get c equals -1/2. So c would have to equal -1/2 in order for this function to be continuous. Okay, problem 21. Write a rational function with a vertical asymptote at x equals 5, vertical asymptote, a whole at x equals -1, and a 0 at x equals 3. And we should not have any parentheses. So first of all, it's a function. I'm going to put f of x equals, so I don't forget that later. Okay, vertical asymptote at x equals 5. That's a non-removable discontinuity, so there would be an x minus 5 in the denominator and nothing to cancel with in the numerator. Okay, a whole at x equals -1 would mean I'd have x plus 1 in the denominator, but there will be an x plus 1 to cancel with it in the numerator. A 0 at x equals 3 would mean the numerator has a 0. So we're going to put x minus 3 because remember when we get horizontal tangent lines or anything, we're looking for a slope of 0. So that would make that equal 0. And then from here it says we can't have any parentheses. So if I multiply that out, I'll get x squared minus 2x minus 3 all over x squared minus 4x minus 5. So that would be a possible function. All right, last one, 22. Find the limit as x approaches infinity, 5x over the square root of x squared plus 3. When we're finding the limit as x approaches infinity, we're comparing the degrees, but I can't yet because one has a square root and the other one doesn't. So if you remember, my trick is to square it so I can square root it. So we now have the square root of 25x squared because I have to square both parts, divided by the square root of x squared plus 3. I now can write it underneath one big square root. Now, comparing the degrees in the numerator and the denominator, they are the same. So the ratio of the leading coefficients is 25 over 1. I still have a square root though. So the square root of 25 over 1 is just 5. So that is my limit as x approaches infinity. And I've answered all your questions.